In this lecture, let us discuss about how to use different kinds of instrumentation to perform aerodynamic studies with some very few simple examples associated with low speed as well as high speed tunnels. Let us begin with low speed wind tunnels. We know that velocity is generally calculated from pressure and it need not be directly measured in low speed applications. We can make use of the pitot-static tube, and the difference between the dynamic and the static pressure would give us the local velocity. However, we may be required to directly measure the velocity fluctuations in a turbulent flow field, in which case pitot-static tube is not the appropriate instrument. You may need to use the hot wire anemometer. Sometimes you may also be required to make measurements of skin friction coefficient, in which case we use a device which is called as the Preston tube. Therefore, we need to have knowledge and availability of alternative instrumentation for the kind of experiment that we plan to do. The instruments that we use broadly are categorized into mechanical and electronic, that we have discussed in previous lectures also, and we have even segregated our discussion accordingly. We are trying to revisit many of the points here and trying to gather the details together from the perspective of performing actual experiments. When we talk about examples of mechanical type instruments, we may be talking about liquid level manometers for pressure measurement, then mechanical balances for measurement of forces and moments. However, as we know, they lack fast response. We cannot have high data acquisition rate, which are important when we are looking at unsteady and transient situations. Many of such situations do exist in the aerodynamic domain, and therefore, use of electronic equipment does become mandatory. Electronic instrumentation can typically comprise of transducer or sensor, signal conditioner, and data acquisition system. The transducer senses the physical quantity. It may be pressure, force, velocity fluctuation, temperature, and other things too, and delivers a proportionate electronic signal to the signal conditioner. The signal is amplified, filtered, and then made acceptable for the data acquisition system. The data acquisition system could be an oscilloscope, digital display unit, PC, etc. When we start to plan for experiments in a low speed wind tunnel, the whole exercise should begin by calibrating the tunnel. At first, the relationship between the speed or RPM of the fan which is running the tunnel and the corresponding test section air velocity needs to be established. Now, we already talked about application of pitot-static tube. We are revisiting it. So, it basically has two ports, one which is at the leading edge senses the stagnation pressure, the other which is on the side wall some distance from the leading edge measures the static pressure, and when they are differentially connected to the two limbs of a manometer, then the difference gives us the dynamic pressure, half rho u infinity square. But that does not come directly, it comes through a measurement of delta H. So, if the density of the manometric fluid is rho, then delta H rho g can be equated with half rho infinity u infinity square, where this rho infinity is essentially that of air. Now, we can write the velocity, the incoming velocity u infinity in terms of the delta H that we have measured through this expression. So, these were all discussed earlier, we are just recapitulating. Now, this gives us the idea that if we have set the speed of the fan to a certain value, then for that value this is going to be the velocity that we attain in the test section. Therefore, by repeating this procedure, by setting the fan at different RPMs, you can get different test section velocities and a consequent distribution thereof. You can see the actual data and a linear fit which are not far from each other. Therefore, by and large you have a linear behavior. This is actually taken from a particular wind tunnel, actual wind tunnel data. Apart from this, uniformity of the cross sectional velocity distribution in the test section is obtained by traversing and locating the pitot-static tube at different locations of the test section at a certain axial position. This basically means that if this is your wind tunnel and this is one cross sectional plane in the test section, then the pitot tube is inserted first at a location which is along the center line. So, let us say this is the center line and this is the flow direction. So, you can move the probe from one location to the other, covering the entire cross section by planning for a certain array of points where the recording would be done. And then you try to test how uniform the velocity distribution is. Another thing that one needs to test is that if this is the side view of the test section, that means if you are looking at the test section from here, then how does the velocity distribution look like? What portion of the test section sees a uniform velocity profile? So, these are checks one needs to do to ensure that you have a high quality flow. Again, remember that you need to check how the properties change along the center line. That is another very important aspect of calibrating the tunnel. We will come to that discussion later. So, that is the next point basically over here, where we say axial variation of velocity along the test section length. That needs to be obtained by locating the pitot-static tube at different axial positions along the center line. So, these are very important activities before you can actually start doing the experiment. Another way of addressing the issue of checking uniformity of the velocity is of course a much more advanced method of using PIV. We had looked at an image like this earlier, and here though the color changes look quite dramatic, you have to remember that the range within which they are changing is not all that large. It is just between 7.9 to 8.1 meters per second. However, the problem is that if you want to do the cross sectional view, then it becomes more difficult for doing a PIV, because it is very difficult for the cameras to view from that angle. Next that you need to look at is flow angularity. It is the angle between the wind tunnel center line and the local velocity vector, both in yaw and pitch sense. It can be measured by different means. One could be a multi-hole probe, or it could even be a pitot tube which is pre-calibrated at different angular orientations. Finally, whatever instrumentation you use, a very high quality wind tunnel should not be having an inaccuracy more than about plus minus 0.2 degree in yaw as well as pitch. So, that is flow angularity. That is so very important, because if you are testing an airfoil, for example, by mounting it in the test section, you need to know this, because if you have set it at 0° angle of attack, but the flow is actually coming in at a different angle, then the whole data will be erroneous. Longitudinal pressure gradient. This needs to be measured in order to find out what is called as horizontal buoyancy, which act on the models if there is a pressure gradient along the flow direction. That means the front portion of the model, if it is a large enough model, may be facing a certain pressure, while the back portion of the model may be facing a lower pressure, and thereby there is an additional drag which is caused because of the pressure gradient which is there in the test section, which ideally should not be. Now, such corrections also have to be implemented in the data that you get out of such a measurement. It can be done by traversing the pitot tube or by using a long static tube with static pressure rings located along the length of the tube. Test section turbulence intensity evaluation is also very important. So, either you do it with a hot wire probe which is attached to a hot wire unit for acquisition of the data and processing it, so that you can get the information about turbulence intensity from the measurements. Before the advent of hot wire anemometer, there used to be a very popular technique called as turbulence sphere method, which is still in use, where you have a smooth sphere with 4 evenly spaced pressure ports in the aft region, and the sphere is sting mounted in the wind tunnel flow, and based on the pressure readings from the 4 ports, an average value of turbulent intensity in the test section can be estimated. So, these are different aspects of wind tunnel calibration which one needs to be aware of. Now, for a very simple experiment one may think about, that is trying to find out pressure distribution on a 2-dimensional geometry. It may be an airfoil, it may be a circular cylinder or other geometries. So, to keep the geometry simple, a circular cylinder model, for example, can be easier to fabricate. If you have a standard circular metal pipe, if you polish it well, then it can be cut to a suitable length according to the width of the tunnel and then appropriately mounted on the walls of the tunnel, and it should be mounted normal to the flow direction. And then small pressure ports may be made on the surface of the model, and below the ports you need to have small metallic tubes attached, to which again matching silicone rubber tubes have to be connected. That means, we are finally talking about small pressure ports on the surface of the cylinder. So, let us say this is a portion of the surface of the cylinder. You have a small port to which a small metallic tube is attached, and then you have a matching rubber or silicone rubber tube better connected on one end, and on the other you can make an adapter, which is basically a metallic adapter which can accommodate the small diameter silicone rubber tube on one end, and it can accommodate much larger rubber tubes on the other. These much larger rubber tubes will actually go to the manometer end. So, very often we need such metallic connectors which can accommodate rubber tubings of different sizes. At the model end, you cannot afford to make the ports very large and use the same large diameter tube for the measurement, because the measurement will become extremely inaccurate. Therefore, you need to use small diameter rubber tubes on one end and larger rubber tubes at the other end, using a suitable metallic adapter in between. So, we talked a bit about the pressure ports and the tubings that you need to have, and then you can make these measurements. The front stagnation point of the cylinder would record the stagnation pressure, while any other orientation of the port will record the local static pressure, and both of them are represented in a differential sense with respect to the P infinity. And once you perform this experiment for a range of angular orientations, you should be able to get a Cp versus theta plot for the experiment that you have performed from 0 degree to 360 degree of the cylinder, and then you can try to compare it with the theoretical expression that you have learnt earlier for inviscid flow. And we have already discussed it earlier that the theoretical distribution goes somewhat like this, where at the stagnation point it is 1, that is the front stagnation point. At the rear stagnation point it dips as low as -3, but when it is the experiment that you are conducting, then you will find that though in the near to the stagnation regions the pressure is somewhat comparable, as you approach the rear part of the cylinder the pressure distribution becomes very different. So, this would be basically the trend of the experimental data, and then you know that this behavior is because of the flow separation which occurs in the rear part of the cylinder because of the adverse pressure gradient which is induced on the flow, which is induced, and therefore, the flow is unable to remain attached on the body. And from this kind of a pressure distribution, try to argue that how you can show that CD is greater than 0 while CL is still 0. It is a non-lifting body. So, this is a very interesting experiment. For airfoils, on the other hand, you could also go for angle of attack variation, which is going to add another interesting part to the story. Like we can see over here, where you have a low aspect ratio square planform wing mounted in the test section, but now we are moving to electronic method of measurement. Here it is sting mounted on a 3 component sting balance. That means we have a Wheatstone bridge in place, and if we excite that bridge using a signal conditioner, then when the forces come onto that bridge, then you are going to have voltages coming from the Wheatstone bridge appropriate to the force and the moment. So, when you store your balance, you need to have an appropriate place where it can be stored safely, where the bridges are not damaged. Also, you will find that normally there are attachments which are provided along with the balance by the balance manufacturer, which are very useful for balance calibration. So, when you purchase it from a standard manufacturer, you will get an initial calibration report, but please do not rely on that report if it is being used for a long time. It needs to be recalibrated. So, we have discussed this, that the balance has to be loaded appropriately for calibrating each one of the bridges. This experiment was performed for different Reynolds numbers. In the low Reynolds number range, typically from 50,000 to 150,000, and it is showing you some effect of Reynolds number on the lift coefficient, which is visible especially as your angle of attack goes larger. That means, as you approach flow separation, there are going to be increasing differences. These aspects also we have discussed earlier in the course. Some more on measurements in low speed wind tunnels, where we can see that already we saw the signal conditioner. There we were talking about load measurements. Now we are talking about pressure measurements. So, a lot of pressure tubings are coming from a model which is already placed inside the test section. This is probably a 2-dimensional model, and that is why it is sidewall mounted instead of being sting mounted. And then this is a pressure scanner which is lying over here, which can be indexed so that different ports can be engaged. The indexing can be done with solenoid control or can be manually done. This is a pressure scanner where it can scan on its own through multiplexing, and then you can use DAC systems of this kind to be attached with it. Again, here it is a kind of in-house packaging which has been made, where you can see that a complete module, a standalone module which can be used for pressure measurement. So, what is it comprised of? It is comprised of pressure scanner units. You can see silicon rubber pressure tubes to be connected to the model coming out of the scanner units. There could be multiple scanner units located here for different pressure ranges. Let us say that one is for a low speed wind tunnel application. There could be one for a high speed wind tunnel application where the pressure ranges are of a higher order. There are analog to digital conversion units, and each AD unit is interfaced with a pressure scanner. You have a DC power source for the scanners and AD units. So, all put together in a kind of modular fashion, so that you have a pressure measurement module, standalone pressure measurement module, which can be easily ported to different wind tunnels for measurements. So, these kind of arrangements are very useful when you are doing wind tunnel measurements in different tunnels for different purposes. Now, let us move on for a discussion on some experiments in supersonic wind tunnel. Let us say we are using an intermittent blow down type supersonic wind tunnel, which is most often found in academic institutes, even in research labs. And let us say we set out our goal first to find the test section Mach number, like we were talking about calibrating a low speed wind tunnel. Similarly, in a high speed wind tunnel, the first thing that we need to know is the test section Mach number. And if you have fixed liners in the test section, then you will have one particular Mach number at which the tunnel can be operated, unlike a range of speeds at which a low speed wind tunnel can be easily operated. So, that freedom is not here until and unless you have flexible liners, which is rather rare and expensive. And can you obtain it by various ways? We are trying to answer that question. In the first experiment, we will basically use the Rayleigh pitot tube formula, for which we certainly need to insert a pitot tube into the test section. And obviously, because of the higher pressures that we anticipate, we are going to use a mercury multi-tube manometer, and wall static pressure is going to be recorded from a point considerably upstream of the probe, and that will be connected to one limb of the manometer. And obviously, the pitot tube, which is inserted in the test section, will record the total or stagnation pressure, which is connected to one of the limbs. And you can imagine that what is recorded by the pitot tube is basically the stagnation pressure behind the normal shock, and based on this pressure, which let us say is P02, the stagnation pressure behind the normal shock, and the measured wall static pressure P1, we know that from the Rayleigh pitot tube formula we can obtain the M1. So, though this is not an explicit expression for M1, we can solve it iteratively to obtain the appropriate value of M1. So, that gives you the test section Mach number. This is one possible way in which you can obtain the test section Mach number. Are there more ways? Let us try to explore that. Here, one thing that we need to remember is that the measured pressures have to be expressed in absolute sense. Do not try using them in a differential sense, unlike what we often do for low speed applications. And therefore, in the previous expression, the P02 and P1 that we have used are in absolute pressure sense. Now, we are looking at another possibility of trying to find the test section Mach number. So, where we are going to monitor what is that constant stagnation pressure which is maintained at the reservoir when you are running the test section, and that pressure is measured by using some kind of a board-on pressure gauge, for example, or it could be even a electronic pressure gauge which is mounted on the reservoir wall. So, the P01 that you have over there at the reservoir end and the static pressure that you have in the test section after the flow has expanded through the CD nozzle, has gone sonic at the throat and supersonic after expansion. From this ratio, hopefully we should also be able to get an assessment of the test section Mach number, assuming that the expansion has been isentropic. And the test section now is certainly an empty test section without any probes, etc., which could have caused shock waves. So, as long as you are able to maintain these conditions, hopefully this is another way in which you can measure the test section Mach number. So, we have talked about two possibilities. Another possibility, let us try to explore, is by using a wedge model. Let us say it has a base height c. So, the wedge stands here, let us say with an angle theta, and it has a base height c, and it is placed in the test section, the supersonic wind tunnel test section, which has a height of h, and you have a flow coming from the left towards the right. Now, the blockage, the kind of blockage that it will create in terms of percentage is of course this, which has to be small, without which you can have significant blockage effects on the flow. Not only that, there could be wave reflections from the walls, and there could also be problem of tunnel unstart if the blockage is too high. Now, if you do the experiment, you should be able to obtain the Mach number of the test section again through a means that we are going to see very soon over here, that if you observe the flow field around the wedge, then you will see an oblique shock formed. So, you have information about the theta, and you can derive information about the beta. Ideally, you should be using the value of theta by 2, because that is the compression angle, and the deflection of the flow, which is the beta that we are talking about, and from the theta beta m relation, if you have an attached shock, you should be able to get what the Mach number is. But then how would you really be able to obtain that? Well, one process of obtaining it could be that you use a flow visualization technique, which is the Schlieren visualization, which you might employ. Through direct measurement, you should be able to assess the m infinity again by using your theta beta m relation, as long as the wave is attached. There are other things that you need to note, that is the observations that will come from your experiment. That means whether the pressure coefficient is kind of more or less constant on the slanted wall of the wedge. Again, due to the flow expansion at the rear wedge corner, that means in this region, whether the pressure coefficient in the base region is lower than on the slanted surface or not. You can imagine that in the base region, which is in the rear part, the pressure will be lower than what you have on the slanted part. And also from the Schlieren flow visualization, you should be able to figure out that the darker bands that you see over here are regions of compression, while wherever expansion occurs, the color gets lighter or weaker, and this is the first time the expansion begins, a massive expansion begins beyond this corner. So, strictly speaking, the constant pressure region is where you have the region between the tip and the first expansion corner. So, we already talked about the theta beta m process, by means of which you can obtain the test section Mach number. And there is one more technique that you can finally think about, that is, you can measure the height of the test section, and then if you move further upstream, you know that you will encounter the throat. That is where the liners become very close to each other. The upper and lower liner forms the throat. So, you can also physically measure the A star. So, A by A star will be basically H by, if you measure this as H star, because the cross sectional dimension anyway will be constant. So, based on this ratio again, you can predict what the Mach number in the test section is. So, we have discussed about many possible ways by which you can measure the test section Mach number. So, in this lecture we discussed about how wind tunnel and associated instrumentation are used for performing aerodynamic studies by making use of the theoretical and experimental exposure that we have attained in the course. A few examples were chosen and cited for low speed as well as supersonic wind tunnel for the discussion. Thank you.